Good morning, good evening, good afternoon, everybody. It's my great pleasure to introduce uh, Professor Johan Malmqvist for the 33rd lecture of the CRE group. He'll be talking about the CDIO approach, designing engineering education to address 21st century skills. Johan Malmqvist is a full professor in product development at Chalmers University of Technology, Gothenburg, Sweden. His research addresses methodology for data-driven product development. Current research focuses on methods and tools for design for additive manufacturing, for the application of machine learning in design, and for mass customization of pharmaceutical products. Another area of interest is engineering education. Malmqvist was one of the co-founders and is still active in the International Conceive, Design, Implement, Operate Initiative, the engineering education model that has been developed by CDIO Initiative, that has been developed by the CDIO, has been adopted by a large number of universities across the world. Malmqvist co-authored Rethinking Engineering Education, the CDIO approach, published by Springer Verlag. Thank you very much, Johan, and it's my pleasure to hand over the mic to you for the lecture.
And I hope that it is visible in the right way now.
Yes, it is.
So thank you very much for inviting me here to talk about. So anyway, thank you for inviting me here to talk about this approach to engineering education that we have developed now for almost 25 years. And it started really with a critique of engineering education at MIT, where they had some industry experts involved and saying that we like what you do in research, but we don't like what you're doing in education, because your graduates not having the skill sets that we actually need. You need to change and come up with a new model that addresses some of the things that we don't find in your student, and that included, for example, ability to turn theory into practice, to be team workers, to communicate better, and other things. So that is really where we started, and then we are still along with this and developing the model that we founded in all those years ago. So that's what I will be talking about. And so first I'll go into a little bit the knowledge and the skills that the graduating engineers from universities in this century are needed to have in order to perform well in the workplace. And then I'll go into what are the characterizing features of an engineering curriculum that develop those skills. How can you take a systems approach to designing an engineering program so that it does what it should do, so to speak. And then we go into sort of the design process of design or engineering education. So what tools are there for working with this process? And then I'll have a discussion of some cases or examples, and I'll conveniently take Chalmers Mechanical Engineering program there as my main case, because I am been there, but CDIO is not only about mechanical engineering in our community. We have all over the spectrum of engineering educations, but also non-engineering programs are involved. So it is a general approach, we believe, and that's. But the examples today will mainly come from mechanical. And I'll also discuss a bit what we are, how we are developing the model at the moment, and what's going on there. But just to start with a few words about what we think CDIO is, and we think it is, or we would say that it's three things or three aspects that you can discuss. One is that an idea of what engineering students should learn and how. It is also a methodology for engineering education reform in the form of the CDIO syllabus and 12 CDIO standards. But it's also a community. So we have what we call the CDIO Initiative, and it has something like 180 universities across the world as members. So let's go through and start with the idea in CDIO. We are asking ourselves basically a what and a how question. So I'll discuss them in turn. And so the first question is, what should engineering students learn? And given the critique that we started from, we didn't want to say tweak their then current engineering programs a little bit to say sort of do something that addresses some minor change or so forth, but rather take a look from the start, okay, and ask ourselves, what is the professional role of engineers? What do they need to be able to do, so that we could have a top-down design of our educations. And then we sort of found some quotes that we think sums this up in a sort of a first level basis, and you may have heard them before. Scientists investigate that which already is. Engineers create that which has never been. What you need to invent is an imagination and a pile of junk. Yeah, it's with pictures of Edison's lab and Theodor von Karman.
Yeah.
Yeah. So what we see here is that engineering is about creation. Engineering is about imagination. It's also about a pile of junk. And a pile of junk, you could interpret that as physical parts or so, but you can also consider that to be the technical and scientific knowledge that an engineer possesses. And engineering education or engineers use that pile of junk and their creative abilities to create new things. So that you can say is the top level anchoring of CDIO in the professional capacity of engineers. And then we developed and formalized and detailed that. So the definition of CDIO is engineers conceive, design, implement, and operate complex products and systems in a modern team-based engineering environment. So it's a life cycle perspective that we take, and here one might say that operate also includes maintenance, recycling, retiring, etc., just for clarifying that. And then you could move on and take a look at the life cycle and what goes into conceiving, understanding customer needs, new technology, enterprise strategies, and so forth. Designing, making plans or drawings or algorithms that is the technical solution, so to speak. Then implementing by designing the manufacturing process or coding, testing, and then operating. So engineers will work maybe as specialists in one of these phases. What important for engineering education is also to bring forward an understanding of the whole life cycle, to understand what implications for other engineers and for users are decisions that you make in conceiving or designing and implementing. So engineering education might offer some specialisms in all of these categories, but should, for all graduates, be a good understanding also of the full life cycle. And then we worked a bit with formalizing these basic lists to the CDIO syllabus, which is a long list of competencies that an engineer should process. And it has 5 categories. All right, and one has to do with the fundamental knowledge in a different discipline, in mechanical or in civil or in electrical engineering, which is program specific, that is tailored to that. But then there are also personal skills, interpersonal skills, CDIO skills, skills that we argue are rather similar for all engineering disciplines. So it doesn't differ that much in what you need in terms of personal skills as an electrical or mechanical engineer. You need the similar interpersonal skills for collaborating with your discipline, but also with others. And you need an understanding of the full lifestyle and the context of the programs. So these categories 2, 3, and 4 are those that we have focused on development on, right? Because these are something that have enabled us to collaborate across the world and across engineering disciplines to produce some things that are useful for all. And then the other things, say understanding exactly what a mechanical engineer should do or an electrical, we a little bit leave that to the disciplines themselves. But our efforts have been in 2, 3, 4. So, and then we stop here, we can say that, well, this looks similar to other things, and that you can say the same topics or so come up in ABET or CAB, the Canadian one, EURES, etc. Although those were not existing at the time that we started. So there is a lot of shared views on what engineers should be able to do upon graduation, and that is across the world also. There seems to do the same analysis. What I could say is that the CDIO syllabus is the most extensive. It has several layers, and thus it also provides some support for course development. But in many ways, we've seen that across the world you do the same analysis of what engineers should be able to do. But what these other frameworks do not do is the how to design engineering education so that it actually develops the intended skills. So that's the how question. Okay, so that is something that we believe is these other frameworks do not provide an answer to, and sometimes they are not supposed to, since ABET and other accreditation organizations should just say what, but we have some ideas for the how as well. So then we suggest a vision for a CDIO-based education, and that is an education that stresses the scientific and technical fundamentals while set in the context of conceiving, designing, implementing, operating systems, processes, products, and services. And a little bit more specifically, in a CDIO program, you would see that it has a clear and detailed list of program learning outcomes that express a holistic view of engineering. So that is not only technical, but also takes into account social aspects and sustainability and so forth. In the program, you would find a multitude of student design, build, test projects. One main reason being that we want to develop an education that is as authentic as possible, that is near the real work as an engineer, and that is designing, building, testing. What also important is to in a CDIO education is that of integrated learning. And by integrated learning, we mean that you learn professional skills such as teamwork and communication in the same courses, in the same projects that you develop the technical and scientific knowledge so that you learn to communicate about solid mechanics in a professional manner, or discuss ethical issues when you are developing a new product. We see in a CDIO program that the teachers have what we call a triple competence. That is high scientific, engineering, and pedagogic competence, and that is something that is important for universities to foster along an academic career. And we see quality improvement processes that have higher aims than accreditation. So part of CDIO is also a maturity model for self-assessment and for further development beyond what accreditators in different countries require. Then structuring this, we have formulated the 12 CDIO standards, which are really guidelines for CDIO development. And 2 of them have to do with the goals and the context of the education. Some of them have to do with the curriculum and the courses and the workspaces that are available to students. Some have to do with the teaching and learning approaches, such as integrated learning, active learning. There are standards for faculty development, for faculty CDIO skills, as well as teaching skills. And there are a couple of standards for skills assessment and program evaluation. So taken together, these provide support for the key elements of a CDIO program. And this is an extremely busy chart, I know, but there is so to say more under each of these and more specific instructions for all of these that are helpful as guidelines for those that are developing CDIO programs. So let's move on and look at a few examples. And like I mentioned earlier, these are from mechanical engineering at the Chalmers, my home university. So one of the key elements of a CDIO program is that a multitude of design implement experiences, and what that is essentially an instructional event where the learning takes place through the creation of a product, process, system, or service. And we find that there are 2 main arguments for them being the sort of backbone of a CDIO program. And one is that they train authentic engineering and decision making, that is creating things, testing things, simulating their performance. But it also provides a natural context in which you can train other generic or professional or soft skills, if you prefer, including teamwork, communication, ethics, that are also critical for graduating engineers. So here is one example of a design build test project, and that is a car that we developed for where it's in a competition where the goal is to drive as far as you can on 1 liter of petrol. So we're going along from sketching the outline of the car body to simulating the flow around it, to manufacturing in composites and designing and manufacturing the engine, testing, ultimately competing. So that's one example of design build. But then in a CDIO program, you would also find a multitude of design build projects. And basically what you want to is to have a progression and a variation of design projects across your curriculum. So in the first year, you might start with an introduction to mechanical engineering, where nothing much is assumed in technical knowledge from the students, but they can do a creative and conceptual design and do some prototyping and some qualitative evaluation maybe. But then when they come to the second year, they have learned some more maths, some more solids, some more mechanics, and then a project that could be moving them further, could have a focus on design for manufacturing, doing more advanced prototypes, more simulation, having a company as customer. Next step could be a project where they take apart an existing product and redesign it for multiple objectives. And then in the fourth year, there could be a number of elective project courses to choose from with a direction towards mechatronics or automotive or regular products in this case, and then bringing in business objects, having cross-departmental team. But the main point here is that there should be a progression, there should be a variation to develop the students' design build skills. In a CDIO program, you would also find engineering workspaces. Our large course is the prototyping laboratory, and you have various kinds of machinery for metal machining, woodworking, rapid prototyping, water jet, etc., composites. In our case, this is used by students from the first year doing the very simple prototypes, but then along in the fourth there is the extensive use of the water jets and the CNCs and the composites manufacturing facilities that are more demanding in terms of the production. So, and then a second main characteristic of CDIO program is the use of integrated learning experiences. And that's something where we aim to develop both technical knowledge and generic skills in the same course or same instance. So figuratively, students are acquiring technical knowledge and growing in that sense, but they also growing as with regards to development of generic skills and being more skilled at that. And this chart provides a number of examples of such integrated learning experiences. So in the mechanical engineering program, there's an intro to mechanical as a first course, where the students do the design build project that we saw first, but they're also training in communications, teamwork, sustainability, and ethics that is built into the course. Other examples relate to sustainability, which is considered in one specialized course, but it also is an element in many others, in materials and manufacturing technology and thermodynamics and so forth. And these courses are also coupled together through, for example, common commutation labs in math courses and applied mechanics courses or integrative products. So to summarize that, if you want to develop a new engineering program or improved program, you'd want to take a look at many things. So the curriculum, teaching and learning methods, design and implement experiences, learning assessment methods, faculty competence, and so forth. So we have also found that to take into these account, you need a systematic approach, okay, which is a design process in itself. So the CDIO development process starts from some of the things that I've just elaborated on a little bit, and that includes the CDIO syllabus, which is a what, okay, so what skills do you need to develop, or rather from the CDIO syllabus, an individual program will make a selection of those that are relevant for them. And then the CDIO standards provide guidelines for how to design curriculum or for how to design design build experiences, and so on. We have a process for driving that from start to end, and there's also we have also developed a tool for self-evaluation, so you can follow your progress along from the implementation of the CDIO standards, and which is a kind of a maturity model and continuous improvement. I won't go into that so much now, but I will be happy to take any questions on it, of course. What you would do when you develop a CDIO program and you have the CDIO syllabus as one tool for stating the program learning outcomes, there will certainly also be pre-existing conditions, what you already have, your national rules, your university rules, and so forth. So you would start by understanding what the status is of your curriculum with regards to new competences needed and so forth. Then you can design a curriculum, and then as a preliminary, then there's a step of planning the integration between the courses and the learning sequences, and then the outcome is an integrated curriculum. So, but the first step that you would do, or things you do if you're designing a CDIO program, is take a look into what is your high-level design of the program, something that may not have been questioned for many years, being built into the walls of the system, highly dependent on the competence they have, or the competence of your professors, who may be rather conservative in the view of changes for different things. So what you really want to know is to get a view on what you want to, the idea with the program, what is it supposed to stand for, what are the professional tasks and roles of our graduates, to understand that. It might be that you have a focus on a specific life cycle stage, say conceiving, if your program is, say, more towards the early stages, but it may also be that your program is more focused towards operations, okay, and that will influence the contents and of course. And then you would take a look at what are going to be our main principles underlying the program design, and that might be that it is should be CDIO based. It can also be that you have a particular approach to mathematics education, that your program should be project based, should it be lab intensive. That's another high level strategy or set of strategies that should be formulated. And in the bottom end, trying to find out what is the competitive advantage of our program as compared to other mechanical engineering programs in the country, for example. So one thing that you would then go is to dig deeper into the customization and detailing on the program learning outcomes, where the CDIO syllabus could be a support, but then there's also a need to develop them and make them more relevant for your own context, and that goes into disciplinary knowledge, for example, as well as CDIO knowledge. So a mechanical engineering program would state some learning outcomes that have to do with the use of the finite element method, but it would also have goals that are related to product design, for example, to be able to evaluate product suggestions based on many different criteria. And with those in hand, we can develop something called a curriculum design matrix. So this is a matrix which features a mapping between the program learning outcomes and the various courses that you have in your curriculum. So you can see where each of the program learning outcomes is addressed, So, and the point here is that you can see that you have considered all of the program learning outcomes. You know what they should be taught. There might also be cases where you cannot really find what a particular course in your preliminary curriculum contributes to, and that could be a reason to question why that course should be in the curriculum. Is it just for tradition, or is it the fact that the program learning outcomes need to be modified a bit to provide that? So, and then after that preliminary mapping, where you have some of your goals, we can take a look into planned learning sequences. So, and by that we mean the sequence of the learning of a particular program learning outcome across different courses in the curriculum. So when on this chart we see that the vehicle engineering program at KTH had a goal for written communication, and that was planned to be taught in the intro course, in a physics course, thermo, and in the bachelor thesis. So with that kind of planned learning sequence, you can understand how you might have maybe a technical report in the intro course, a lab report in the physics or thermo, and then something other to do with a bachelor thesis, which is a longer report. And if you look at these planned learn sequences, you can see that things do progress from one course to another, and it's not the single teacher that is teaching us, but rather it's, in this case, be at least 5 courses that are involved and 5 teachers that take responsibility for developing these skills. So, and this is just another example of the same kind of thinking. Communication in English is, in this case, taught in 3 courses in their program. So that were a few glimpses into what a CDIO program is. Now to move on to see what are we doing at the moment. And one of the most influential reports on engineering education recently has been Ruth Graham's Global State of the Art in Engineering Education from 2018, where she identified a number of elements that are growing in importance within leaders in engineering education, including a combination of digital technology and active learning, increased students' choice and flexibility, curricula that bring together multidisciplinary learning, global experience, the use of engineering to drive positive societal change, role responsibilities, ethics of engineers, and a breadth of student experiences. So when they're taken together, we see that there is a development of engineering education from the traditional way, that reductionist, emphasizing engineering science and mainly research and development, not so much manufacturing or operating, much on analysis, through the CDIO as it was in the when we started development, adding on the dimensions of the product context and much designing, a team-based approach. But we are now moving more towards a challenge-based view of the engineering process, and then we're bringing in a societal context, start a bit more upstream, actually not with a given problem, but rather problem formulating and designing, and where values are important as customer needs or societal values. So, and then important elements in CDIO programs then become challenge-based learning experiences. And then the learning takes place through the identification, analysis, design of a solution to a social technical problem. And that requires multidisciplinary teacher teams as well as student teams. It might be placed in an international context, development of something in collaboration, and with consideration of environmentally, socially, and economically sustainable. So those have inspired us or driven our development recently. So for the most recent versions of the CDIO standards, we brought forward more strongly sustainability, services, digitalization, faculty competence, and also added some additional. So in fact, the standards are actually 16 now rather than 12. And those included also sustainability, mathematics, entrepreneurship, internationalization. Along with that update, also the CDIO syllabus was updated. So the things that are more prominent in the recent version of CDIO syllabus have to do with sustainability, more details on environmental sustainability, but also a stronger representation of social sustainability. Also saw a little bit of a change in the view that we have seen on teams, where earlier we would consider the student teams to be say smaller or smallish and solving a different problem, but now it's also teamwork and collaboration, so a little bit broader view on that. Digitalization, AI and so forth, and also what we call acceleration, formulating skills needed to work in complex or VUCA environments, and a stronger emphasis on self-learning skills to be able to adapt your competence quickly already when you're in the workplace. So a couple of examples on that, and one is that what is Chalmers known as C Labs, or where C stands for challenge, and it operates a master level course open to students from all of Chalmers programs, and is carried out in collaboration with regional societal actors, and has a specific facility which is just outside of Chalmers, intending to provide a neutral ground for the collaboration with the regional and city planners that are part of the setup. And then this picture shows sort of the course design, which has two main components, and that is one, understanding the theme or the setting, and then one that has more to do with the conceiving, designing, implement. So this is something that 20 students would take, and they would be earlier giving a theme and a set of collaborators, stakeholders from the outside of the universities to understand the theme, which might be to develop something, say, urban transportation in the Gothenburg region, through dialogues with stakeholders, understanding what subtopics need to be addressed in that, formulate the problem, learning about entrepreneurship to, in this case, a social kind of entrepreneurship, and then splitting this up into a number of different projects that still collaborate across the master thesis period. And another initiative that we have developed is so-called tracks, and the idea is to use them as vehicles for enabling more multidisciplinary learning in the program by creating courses that are electable for students from different programs. And a student can pick one or several of these as a complement or a credited part of their programs, of course. And these are formed in a number of themes. There's about 35 of these courses at the moment, but AI, sustainable transportation, health and sports, technology, other things that with the common thing that they are open for students from all programs, and also supported by a new common learning lab, which is an extension of the concept of a prototyping lab, and includes on one hand things for prototyping, but also various other things for sports technology and a richer environment for the development. So this brings me to the end. So what I would like to say there that in CDIO we have developed a model for engineering education, and it addresses both the what should engineers do, but also the how. And and we think that the how aspect is the something that is not really found in other places. So we are showing how programs can be systematically designed to address all intended program learning outcomes. We show how you can connect learning of professional skills, like learning of disciplinary knowledge. We emphasize the importance of design implement experiences throughout the curriculum, as well as the training of faculty members to teach engineering knowledge as well as professional skills as an important element and a very tough challenge for universities to arrange. We have done this in collaboration, and more than 180 universities worldwide are members of our initiative as it is. So we also argue that it is a relevant and proven approach, and keeps on developing. So by that, thank you for listening, and I'm happy to take any questions.
Thank you very much for really going through this entire program. It's of great value to a lot of people who are thinking about it to implement how to implement uh, theory practice education together. One question I have is, from your experience in different countries, what kind of impediments do you think they have faced, which they had to deal with in order to implement such a program? I'm sure even at Chalmers in the beginning it was not easy. It would have taken time for you to come around the barriers to get to where you have gotten to.
So there are certainly some barriers. Some could be financial.
Mm-hmm.
So we have an element there that you want to create engineering-like workspaces for your students so that you can do that. Okay, and that can cost money and so forth. But our experience is also that you can also create low-cost engineering workspaces that have a high degree of functionality. So that doesn't have to be as expensive as some of the larger labs that are have been developed and built in at MIT and other places. So that's something I think you can work around.
Mm-hmm.
So another challenge is that of faculty competence.
Mm-hmm.
And faculty tend to be hired and promoted based on their scientific knowledge, and that might you might be the best person in the world on an aspect of thermodynamics.
Mm-hmm.
Certainly a very capable person, but you may not have been actually designed anything.
Mm-hmm.
So that could be something that is problematic because you don't have the competence within the faculty to teach something like design or
Mm-hmm. Mm-hmm.
also communication and so on. So that's something that would need to be considered both in hiring faculty,
Mm-hmm.
but also in opening up opportunities for training along the way. So when we've done surveys amongst our members, the development of faculty competence is frequently mentioned as the
Mm.
something that is difficult and that is ongoing because it's a little bit yeah, people
It's a
are
cultural change.
merited for other things, and then
Yeah, it's a
you need to
cultural
make them
thing.
prioritize this as well.
Right, right, right. Makes sense. But have you observed, it's a side question, which is over time, as people have started getting into this program, even those who did not design and were purely thermodynamists also started participating in a way they could see that would benefit them.
Um,
I'm
I'm not,
curious. You
yeah,
don't have to answer. Yeah.
no, no, I'm not sure actually, but we've always tried to work with the enthusiasts and
Hmm.
not do too much of turning around someone who doesn't have the
Okay.
interest.
Okay. Just curious as to how you went about it. That's all. Yeah. Sudhir, go ahead. I'm done. If anybody else has questions, please put them in the chat or raise your hand or ask the question.
Yeah, from the audience, anyone has any questions, please go ahead.
I don't see any. Why don't you go ahead?
Yeah, there is a question from Professor Vasa which says, how much emphasis is placed on hands-on activities?
Mm. Hands-on activities are important in a CDIO program. And then by hands-on activities, we would mean things like prototyping, developing prototyping, as well as hands-on activities for, say, measurement or learning from the things that you do. So I think that's important for many reasons. Prototyping, you want to learn that in order so you dare trying out your ideas. There's also an important element of learning from the surprises of something that you have prototyped and then you test it. There's things there that you cannot really learn from simulations only. The expecting and also the excitement of something that is working. So that's an important part. But hands-on should also mean hands-on in the by the use of simulations and so on. So it's not only physical prototyping; it's also digital.
One question I have is the challenge-based. There is a related question. I think in the chat there is a question which says, can we have laboratory in parallel or sequence along with the theory courses?
Yeah. I'm not sure that I understand the question completely, but one of the things that we have also sort of tried to say that you should not sort of always learn all theory first and then do the practical stuff, because that was a trend in engineering education and meant that practical was pushed further and further up in the curriculum, but rather that you have both theory and practice in the from the very first start. So including simple product development projects in the first year or even the first semester, so as to be able to have a progression also in these skills. Okay, then you cannot put them all at the end.
You have mentioned about the shift towards challenge-based problems or challenge-based learning.
Yeah.
So how different was that compared to the previous one, and was it applied at the undergraduate level?
Yeah, the example from with the collaboration, the C labs, that's on the master level. But there are many other examples of challenge-based courses that are also from the undergraduate level.
So do they come in the advanced years, or do they come throughout the program, or how does it work?
Yeah, I think you could do that from. I have written a paper on that, and there is a comparison of 4 different challenge-based courses, and one is actually from the first year, another is from the second, the third is the C labs that I described here is on the master level, and then there was also one from DTU, which is for master thesis projects. So that can be done on in different stages of the education when arranged properly.
Also, could you throw some light on the integrated learning that you have talked about, the technical and professional skills? Because some of the professional skills cannot possibly build within a semester. It takes some time.
Yeah.
How is that integration done to enhance these skills over a couple of semesters?
Yeah. So if you take something like written communication skills, and in the example that was in the slides from KTH, there were specific elements of written communication in 5 different courses during the bachelor period, and then when we say that there were, we would distinguish between some where a skill is taught and where it's utilized. So in these courses, they will all be taught, meaning that there is some lecture, there is some assessment on the skill, and what you would, and then other courses you might write a report, but it's not assessed for its written communication level. But then you could have a plan between these different written elements, say a sort of descriptive report, a lab report, a memo, an extensive thesis report that are a bit dissimilar, so that you have a planned development of that particular professional skill. And that is what we would call a planned learning sequence. And you can do that for written communication, for oral communication, where you also arrange it so that different things are taught. Because a common pattern that we have seen is that there's a restart of development of these skills. Okay, so someone teaches that, but without communication to the next teacher in the sequence. The teacher number 2 does basically the same as teacher number 1, and then maybe even teacher 3 repeats. So you want to have a program perspective on that, and an awareness from the different teachers what is their contribution to the whole.
Yeah. So a related question is, this also calls for a reasonable amount of collaboration between faculty across the semesters and within a semester. So are
Mhm.
there any institutional mechanisms that are used to support this?
Mm. Yeah, we do emphasize that you should have um, a strong program leader or head of a program who is the architect of the program, but also has the important role of bringing together the teachers to a teacher team. So, because if you don't have that role or responsibility, tendency is for teachers to take, this is my course and I'm doing it as an island, and I can do it well and don't disturb me so much. But that is not really the idea of an integrated program. In an integrated program, teachers collaborate with other teachers with other courses. And then in order to make that happen, you need to have a strong program leadership and with the responsibility for that. That's a big, it's a challenge for sure.
I suppose along with the financial mobilization that is required, and sometimes the evaluation process for those people who participate in the integrated program from the traditional faculty evaluation. I'm sure those are the kind of things you also face.
Yeah, so I think that so the academics, if you leave them on their own, would tend to sort of go to their discipline and work on their own stuff. But an engineering program is not something that you can do just as
Mm-hmm.
freestanding modules. There is something which is a common whole that is needed, and it's also a job for the university to make their programs work
Mm-hmm.
in that way. So that, although that is challenging, it's something where you need to put energy into to continually do that and keep on doing it over time.
Mm-hmm. So you're building a new culture altogether from one before. Thank you very much. Unless there are any more questions, it's been a wonderful talk. I really enjoyed the overall approach of designing a system from conception to evaluation. I think it's a very good example of systems engineering itself in the educational context. And we'll keep in touch and see, maybe sometime you can even go to India and talk to some people.
That would be great as well.
Is there anybody in India at the moment participating? I saw a little dot in your map, but I wasn't
Yeah.
sure.
So we have a number of Indian universities as member as well.
Oh, okay. I might ask you at some point to give us a list of them, just to so that other people can learn from them or talk to them as well.
Yeah. So just send me an email and I can do
Yeah.
that.
Sure.
Anything else? Anybody has a quick last question? You can unmute yourself and go ahead. If not, we will bring the session to a close. And the next lecture is on August 14th. It's going to be given by Professor Jörg Schulze from FAU in Germany. This is his talk number 2. This is a follow-up of the talk called Microelectronics and Bauhaus. The last talk was how they conceptualized it. The next talk, you can see that in the web page. And the next talk is on how he implemented it in building that master's and undergraduate program in microelectronics at FAO, Germany. Thank you very much. With that, I think we can close. Right?
Thank you.
Thank you.
Bye.
Thank you.
I'll see you when I'm there. Yeah.
Yes, will do.